Hi. In a previous video, we looked at the Fourier transform of the Dirac-Delta function. And the result of that ultimately was that if I take the Fourier transform, I'll do a fancy F, of the Dirac-Delta function, we learned that it was a non-zero value for all frequencies, basically saying that all frequencies make up the Dirac-Delta function. And another thing that we learned is that if I were to do the inverse Fourier transform, I would get an expression for what delta of t is. It ends up being e to the j omega t d omega. If you are confused about where this comes from, please see my other video on Dirac-Delta functions. The way that we finished that video was to also say that I can just do a change of variables and say that I can go and integrate with respect to time, and I will get the Dirac-Delta function in the frequency domain. And the reason I'm mentioning these, and I'm going to go ahead and take these, I'm going to make them a little bit smaller so we can have them kind of as a reference for us, is in this video, the goal is to look at the Fourier transform of a cosine wave. Now, I give you a cosine wave that is cosine of 3t. So that means that for this function, this has a frequency of 3 radians per second. And remember that the goal of the Fourier transform is to see what frequencies make up a signal. And in this specific signal, it's only made up of one frequency at 3 radians per second. So we would expect something that has zero values everywhere in the Fourier domain, except at omega is equal to 3. Kind of. Let's go ahead and do some math and show what this is through proof. But that's what I want you to think about prior. What do we expect? And we expect to see activity or some sort of magnitude or presence of omega equals 3 in our answer because of the fact that is the only frequency that makes up this cosine wave. So let's go ahead and use our Fourier transform equation, which is this guy here, and determine what our Fourier transform of cosine is. So in this expression, we're taking our x of t, which is our cosine function. You see that this is a function of time. And I'll put that into my integral. So I'll say that this is the integral from negative omega, or negative infinity to infinity, of cosine of 3t e to the j omega t dt. It's important to note that this 3 is a part of the cosine function. That is the signal that we're interested in. The omega here is just some general omega. This is not equal to 3. This is just a variable. Because at the end of the day, we want a function that's of omega. So if we put in a 3 there, then we would have no omegas in our final expression. So this omega that's in the exponential will stay as omega and not be substituted in as some sort of variable or some sort of value. So we have this integral now, which is kind of ugly because we have a trig function and an exponential. You can do something like integration by parts, but we're most likely going to need to do that twice, which becomes kind of gross. Instead, let's leverage the fact that we can represent this using complex exponentials. And I'll go ahead and show how we do this. But let's just remind ourselves about Euler's formula, or Euler's identity, Euler's equation. This says that if I take an exponential multiply it by j theta, or rather exponentiate it to j theta. This is the same as cosine of theta plus j sine theta. So if we wanted to have something like cosine of 3t, we would plug in for theta 3t. And I would like to have an expression for this in terms of just complex exponentials. And the nifty way of doing that is to look at what happens when we have a negative exponent. If I do e to the minus j3t, I get cosine of negative 3t plus j sine of negative 3t. And what I would like to look at real quick is just a unit circle so we can understand what happens with cosines and sines. But if I have an angle theta, which in this case, let's say it is 3t, the cosine section of that is the horizontal shadow or projection of the vector onto the x-axis. And then the y value to that vector is sine of theta. Now imagine that I draw the same exact vector but with a negative angle. So now I have negative theta in there. Do we see that the projection of the cosine of that vector is exactly the same as the cosine of the positive angle? The moral is that cosine of theta is the same as cosine of minus theta, meaning that these two expressions here are equal to each other, the cosines. While if you look at the sines, you'll see that the sine value are negatives of each other. So that means that sine of theta is equal to, it's not equal to sine of negative theta. That would give us this. We have to negate it. And those are some important identities. With those in mind, I can rewrite this second equation. I'm just going to copy and paste these, and I'll make some changes. I know that cosine of negative 3t is the same as cosine of 3t. And I know that sine of negative 3t is going to be the negative of that. We can also write this one as sine of negative theta is equal to negative sine of theta, which is what we just did here. Now, the beauty of this is now if I were to add these equations together, the j sine 3t's would cancel out. So if I were to add these together, I would get e to the j 3t plus e to the minus j 3t. That is equal to 2 cosine of 3t. And then the sine terms will negate each other and offset. So what that means is that cosine of 3t is e to the j 3t plus e to the minus j 3t divided by 2. And this is an important relationship for us because if we know what cosine is in terms of complex exponentials, we can substitute that into here. And now I'm just integrating a bunch of complex exponentials, which are easier to simplify. I can go ahead and multiply them, add their exponents and such. So let's do that. Let me go ahead and just bring this down so that we can see it. So x of omega is going to be the integral from negative infinity to infinity. And now I'll plug in this expression, e to the j 3t plus e to the j with the minus 3t e to the j omega t dt. And just reminder that this is the same as this. That's what we just saw up here. So now we can do a little bit of algebra. Let's go ahead and distribute the e to the j omega t to both terms, and I'll factor out the 1/2 just so we don't need to worry about it for now. It's going to be e to the j 3t e to the j omega t dt. And maybe I'll write it as two separate integrals, plus the 1/2 will go to both integrals, e to the minus j 3t e to the j omega t dt. That's what we got right now. Now, if I'm multiplying something with an exponent and that something is the same, basically if I have x squared times x to the 4th, I can go ahead and add the exponents. So what that means is I can go ahead and add the exponents for these complex exponentials. This is 1/2 the integral from negative infinity to infinity of e to the j t omega plus 3 dt. Essentially, I just added these exponents and I took out the jt terms because they are in common. Plus 1/2 the integral from negative infinity to infinity of e to the jt omega minus 3 dt. Okay, now we come back to our friend the Dirac-Delta, because if I'm integrating some complex exponential from negative infinity to infinity, I know that these relationships are true. Let's bring these back down here so we can see them. And the Fourier transform wasn't super important. I'm just going to erase this so we avoid confusion. But these other two are important. Because now what this is saying is that if I am integrating with respect to time, which is what I'm doing in the second one, delta at some location is based on e to the jt multiplied by that location. And if we were to investigate these exponentials, we see that those locations are these omega values. So this ends up being 1/2 delta of omega plus 3 plus 1/2 delta of omega minus 3. This is our Fourier transform of cosine. What does this mean? So again, this is in the frequency domain. We're not in the time domain anymore. And I know that if I were to plot some Dirac-Delta function, and if I wanted to move it around, I can go ahead and use a transformation. So if I moved it to here, let's say that this is some value, I don't know, a away, this would be delta of t. A shift to the right is the same as subtracting in the argument, so delta of t minus a. So if we look at this and we're going to plot in the frequency domain, we would see not peaks at 0 hertz, we would see peaks that are shifted. This first one is shifted to the left by 3. So this is at -3 radians per second. Maybe I'll try to map colors. This one's at -3. And then if I go and look at this one, we see we've shifted it to the right by 3. And this is interesting. We predicted originally that we would have some sort of presence at omega equals 3, but we also have a presence at omega is equal to negative 3. This is a consequence of the Fourier transform because we are integrating from negative infinity to infinity, not 0 to infinity. So because of that, we are including negative frequencies. Physically speaking, we're not going to worry about what that means. That doesn't really mean much. Instead, we'll just accept the fact that our original cosine of 3t will have peaks at 3 and negative 3. Now, what's interesting is that the amplitude of this sine wave or this cosine wave was 1, but we see in our math here that we ended up with 1/2 as the peaks in that situation. Well, kind of. Essentially, the amplitude is split between positive and negative frequencies. And that's what the math shows us. That's what we end up getting. So just to summarize, originally I have a cosine wave that has a frequency of 3 radians per second. That is what we were given. And if we go ahead and do the Fourier transform of it and noting the identities that we found from the Dirac-Delta derivation, we will see that our Fourier transform plot, x of omega, will have peaks at 3 and also in -3 because of the consequence of the Fourier transform. And that is something that will happen all the time in terms of symmetry, that we will see a mirrored image across the y-axis when omega is 0 of the frequency content. Hopefully this helps. If you have any questions, please let me know. Okay, thanks guys. Bye.